Physical properties of the alkanes. So the first thing we're going to look at is the polarity of the alkanes. Now we know that carbon and hydrogen have similar electronegativity values, which means the electrons in the bond between carbon and hydrogen are evenly shared. So they are not closer to one atom than the other because neither atom has a greater power to attract. We say that the bonds therefore are non-polar. The electrons are evenly shared, which means the molecules cannot possibly be polar because there are no polar bonds. Now, when we have non-polar molecules, we are going to be looking at intermolecular forces. So we're talking about molecules. So we say that their structure is simple molecular. And we're going to be talking about intermolecular forces between the molecules. And because they are non-polar, they have the weakest type of intermolecular forces. They have van der Waals force between the molecules. So when we get asked a question about their physical properties, we need to refer to their structure, simple molecular, and their intermolecular forces, van der Waals forces between the molecules. These are really weak intermolecular forces, so that means that our alkanes will have relatively low boiling points and melting points. And it turns out that the first four straight chain alkanes, only with their van der Waals between the molecules, are gases at room temperature. So the next thing we're going to look at is their solubility. So to dissolve, you've got to understand that to dissolve you need to make attractions to water. Water itself has hydrogen bonds between the water molecules. Already says between the hydrogen bonds. And they're much stronger than the van der Waals in our alkane structure. Which means that if our alkane was to dissolve, it would need to overcome the amount of energy required to break the hydrogen bonds in order to make attractions to the water. And it just can't do that. It's got these weaker forces between its molecules, so it can't interrupt the hydrogen bonding between the water molecules, and therefore it cannot get in between the water molecules, which is what it needs to do to be soluble. So the next thing we're going to look at is the boiling point, first of all, of the straight chain alkane. So by straight chain, we mean things like methane or ethane or propane or butane or pentane or hexane and so on. Methane you can't really draw a skeletal formula of. As we look at this graph, what does this graph show us? It says as the length of the carbon chain, which is as we go this way, as the length of the carbon chain increases, we can see that the boiling point also goes up. This graph has got positive correlation. But why is that? So why does the boiling point go up? So remembering that they only have van der Waals forces between the molecules, but as the molecules get bigger, as there are more carbons, then what we can say is that there are going to be more electrons. Remember, van der Waals is the movement of electrons creating a temporary dipole. So because as they get bigger, there are more electrons. So I might just write that. As the size of the alkane increases, there are more electrons in the molecules. So the van der Waals forces between the molecules are stronger and require more energy to be overcome, to break. And so that boiling point increases. Our next thing is looking at the shape of the alkane. So these alkanes are all, so these are isomers, so they're all C5H12, but we've got pentane, which is a straight chain, and as we have many pentane molecules, they're going to line up perfectly with each other It's like flat Lego pieces. They're just going to stack one on top of each other. But if we look at methyl butane and then we try to put them close together, they can't get as close together because of the branch. And then if we look at dimethyl propane, because of the double branching, again, the molecules just cannot get as close together. Imagine holding magnets just that little bit further apart. Because of this branching, the attractions are going to be weaker. So look what's happening to the boiling point. So we've got no branches in pentane. We've got one branch here, and we have two branches. What is happening to the boiling point? The boiling point, as we go from no branches to one branch to two branches, the boiling point decreases. So as the number of branches increases, the boiling point of the alkane decreases. So why is this? So there are fewer points of contact. So look again at my structures. Where there was no branches, the alkanes are just packing on top of each other, and wherever they're touching, then points of contact are happening and forces are occurring between the molecules. As we get more branching, there are fewer points of contact between the molecules. And so the van der Waals forces between the molecules always remember you must say between the molecules when talking about intermolecular forces. They're going to become weaker. It's like you're holding the magnets further apart and require less energy to break, and that is why the boiling point decreases.